All right, so this is our third and final part of our series on reverse engineering machine code. In this lecture, we're going to be talking about various code visualization tools and techniques. We'll cover a few different debugger topics and then wrap up with some more advanced reverse engineering techniques. So one of the important techniques to learn is how to best visualize the code and data that you're trying to reverse engineer. In any given program, an average program may have tens of thousands, if not millions of lines of assembly code, a large percentage of which you don't really care about. But by visualizing the data in different ways, it can help you more quickly find that information you care about without actually having to go through and reverse engineer every single instruction in the program. So we'll start here. This slide shows a picture of IDE Pro Interface. And IDE has three different main views for looking at the code. There's the text view, which is basically a linear listening to the code. There are some arrows that show control flow, but it's basically just a big dead listing of code. There's the graph view, which is what you see here, and the graph view is nice because, like, when you're looking at a function, you can see, for example, here the green lines mean that the condition that's being tested is true. The red ones are false. And then over to the right, there's a little graph overview window, which kind of shows you the, helps you navigate kind of quickly around the control flow graph for that function. So this is particularly useful if you're just kind of quickly getting a feel for the control flow of a function or where the real meat of it is, and if there's a lot of loops and stuff, that'll become evident just by looking at the graph. And so there's also a proximity view, which shows more data flow type relationships. So that's looking at the code. There's also a whole variety of these tabs that you see, hex view, imports, exports, and this shows you different views of other aspects of the program. So the hex view, obviously, as the name implies, is going to show you all of the just raw text bytes for the program. There's structures, there's imports, all the imported functions. So all these things will help you examine the program and more easily pinpoint the functionality you're trying to find. So here's another set of two programs. Actually, in this case, we use a combination of PiMay and the UDraw graph program. PiMay is very powerful. It's an open source reverse engineering framework. There's a variety of tools that are part of it, some of which we'll be talking about later in the lecture. And then UDraw Graph, which is a nice graphing program. There are actually a couple different graphing programs that you see pop up a lot in reverse engineering. UDraw, which is we're looking at now, as well as Win32 Graph. The IDE Pro actually uses WinGraph32, and so does this OliFlow plugin, which we'll see actually on the next slide. But in this one, this is very similar to what you just saw in IDE. We see the red and the green arrows, indicating whether or not a condition was true, and just another way of looking at the code. These graphing tools, in particular, come in handy when you're writing your own analysis tool. So you're doing your own analysis, and then you want to be able to visualize those results in some meaningful, useful way. And that last part is key because oftentimes when you are doing different kinds of analysis, you wind up with a lot of data, and it's very easy to load it into some visualization tool and then have a big mess. For example, on this slide here, this is function graphs in OliFlow. Now this is a useful thing to look at because you can, by kind of zooming out here, you can get a sense of the whole call tree, which functions are called. If there's functions that are called by a lot of different functions, or if there's some that are only really called by one. So depending on what you're trying to do, that view may be useful. But you can also wind up with graphs that are there's so much data you can't even really make heads or tails of it, and so being able to visualize or narrow your focus into something that's manageable that's definitely important. So OliFlow is a plugin for the OliDebug debugger, and it can show you function graphs. And on the next slide here, we show different flow graphs. Again, similar to what you saw in the graph view of IDA, indicating whether or not the different conditions were true or false. So, depending on your preferred choice of tool, you can of course use whatever graphing tools that you want. Symbols. Whenever symbols are available, you always want to load those in if possible. I mean, symbols do help. They relate to visualization in the sense that when you're looking at the code, rather than seeing call and then some address, you see call and then the name of a meaningful function. It also means that the parameters to that function will be labeled. So when you're looking at the assembly, you can see, oh, okay, this is this argument in the API. And so for Windows symbols, you can actually go and just download them directly at the website you see here on the slide. And these are also available for a lot of the Microsoft Windows executables. Symbols are also, if you're looking at a particular application, if it's compiled with debug information, then those symbols may also be available if you have what's called the PDB file, which has that symbol information. So to load symbols in IDE Debug, this is just showing you how to do that. If you go to the Debug tab and then at the very bottom it says Select Path for Symbols, you can use that, give it to the path of where you have all your symbols, and then when you're reverse engineering code in IDE Debug, you'll then have nice nice symbols to look at. And just as an example, if you can see in this particular window, the symbol for get module handle A is shown, and you can see the parameter to that, which is indicated on the screen. And so those things just help reverse engineer things more easily. In IDA, IDA will actually look when you first disassemble the file to see if there was any debug information, and if so, they'll actually prompt you. Do you want to look for it in this locally or on the Microsoft symbol server? Sorry. And down below shows an example of, in this case, symbols have been loaded in, and this is much more easily readable code. Without even, oftentimes just by looking at the functions, especially on Windows, the Windows functions called, you can get a very quickly an idea of what is this function doing. Well, in this case, it's clear just from the name, display grid, what it's doing. But even if you didn't know the function name was display grid, this code is so much easier to look for because you can see, okay, this is the APIs it's calling, here's the parameters, and it's pretty clear just from the code that it's going to be drawing something. And you can also see on the code cross-reference to show bombs, and then it has the location, so where this code was actually being called from. So very, very useful to do if you have access to the symbols. Now we're going to shift gears and talk about kernel debugging. Kernel debugging is one of the more powerful things you can do if you're wanting to actually look at what's going on in the kernel while maybe an application is running of interest, or if you're actually just, for whatever reason, wanting to debug the Windows kernel or a problem that's on your machine. It also comes into play if you're looking at device drivers. Maybe you're developing a device driver, or maybe there's a buggy one on your machine and you're trying to figure out what's going on. But whatever the case, a few things that you'll want to do first is, of course, install the Windows symbols. In particular, and this matters a lot, is for whatever target version of Windows that you're reversing. So if it's XP, make sure you get the XP symbols. If it's Windows 7, get those. And then you also want to install the Windows SDK. And the Windows SDK, if you install it with the debugging tools, will put WinDebug on your machine. And this is a very powerful debugger. And so when you're debugging the kernel, it's great for examining kernel data structures. A lot of this information you can get out of the Windows internals book, which I would highly recommend if you're doing any sort of Windows kernel debugging or kernel reversing. at all, that book is like the Bible for how Windows works. But in WinDebug, you can examine these data structures, and it makes your life a whole lot easier. WinDebug has options for local live kernel debugging as well as remote kernel debugging. Another type, and this may be, depending on what you're doing, this may be the more common case, is crash dump analysis. So whenever Windows has a blue screen of death crash, it can be configured to create a crash dump, and which is this .dmp file. And this basically has a complete snapshot of the kernel state and physical memory at the time of the crash. And so WinDebug also can handle crash dump analysis, and you can go through and traverse the low-level data structures in the kernel. If you wanted to see what processes were on the machine, you can actually traverse the linked list of processes in the kernel, the executive process block or eProcess structs that are there, and so it's quite powerful. And actually, this is a whole topic unto itself. There's books and lots of information online about doing crash dump analysis. In particular, this is if the machine had a piece of malware on it, looking at a crash dump or snapshot of the kernel memory and physical memory is very useful just as a forensic tool, but also trying to understand, trace back to, well, how did the actual initial exploit happen? What was the program that was vulnerable? Was it a browser attack, etc.? So I mentioned remote debugging earlier. Remote debugging is particularly nice for kernel debugging because if you're trying to locally kernel debug and you're single stepping, it's actually going to freeze your machine because the kernel's not doing anything. If it's frozen in your debugger, I mean, you're single stepping and nothing else is happening on the machine except for what you're doing inside your debugger. So with remote debugging, you can have a virtual machine set up, and then that has essentially a little debugging server or remote monitor that can be remotely connected to. And so this is a very common thing, especially like if you have different targets, maybe you have a variety of different VMs, or maybe you're wanting to run malware, and especially if it's doing anything in the kernel, you could create your VM, create a snapshot, so that way you have your sort of pristine baseline, and then connect from your remote debugger, do your debugging, and then if you need to go back, then it's just very easy to revert the snapshot. And so remote debugging is a very good and useful technique to get familiar with. All right, so next we're going to skip over to decoding structures. Structures is another important thing when you're reverse engineering code, especially large code bases. And any good debugger or disassembler is going to let you define different structures. There's the common ones I've been referencing throughout this lecture, Windows internal kernel data structures, which those are well defined in header files. But then there's also, of course, user-defined structures that might be more application specific. And so decoding the structures greatly help in reverse engineering because it gives you meaningful names assigned to variables. So now rather than just looking at a register, the program, the disassembler or debugger may show that, oh, this is actually this field of this structure, and that can immensely help you understand the program. So as an example, in this case we're looking at a PE header, and we're looking here in hex, and we're going to be decoding a section header for the text section. And so how do I know this is the PE header? Well, if you look at the top, one of the kind of giveaways is that you see the MZ, the first 2 bytes, and then you also see the characteristic, this program cannot be run in DOS mode. You see PE further down. So you have your DOS header, PE header, and then some names of some different sections. So just by glancing at this in hex, I know that, okay, this is the header. And so we've highlighted the right at the beginning of the text section there at address 3401E0. So now we'll go to the next slide, and we're going to tell it to decode this memory area as a structure type image section header. The image section header, if you have worked with the PE header, this should be very familiar to you. There's well-defined structures that for all the different parts of DOS and PE header, the different fields. In this case, this is the beginning of the text sections. We're going to say, okay, we're decode it as that, and then here it pops up and it shows. You can see on the right in the comments, this has all the different fields that are part of that structure, and it shows you what actual values are assigned. So this is an extremely useful view, if you're interested in looking at properties for the text section. It also shows you the hex dump, shows you the decoded data, and in this case, the decoded data. Remember that Intel is in Little Endian, so you'll see what was 504-54332 is actually 3243-4550, and that's just putting it in, switching the Indianness around. And in IDE Pro, if you have this shows an example of a custom user-defined func, and so here we just have a simple struct that's been defined with an integer and two void function pointers, and it put in the local types window. And so you can then mark data as having a given structure type, and then IDE Pro will automatically go through and update, it references that structure in the code so that you can actually see the meaningful name for the field that's being referenced. So very useful and powerful tool, especially on a larger reverse engineering task. So function hooking. Function hooking is another powerful technique to get some practice with. This particularly comes into play when you're doing things programmatically. So what you're trying to do here is hook specific events. So this may be function calls, system messages, I/O events, could be anything really that you want to intercept that's going on in the system and perform some additional analysis or handle it in some way. And so there's a variety of functions that go along with this function hooking API, and I've included at the bottom of this slide a link to the MSDN article that talks about hooking in general. It covers all the API and actually shows some useful code examples. So if you're interested in function hooking, I'd encourage you to start here at this website just to kind of see how this is managed under Windows. So this is also useful for things like DLL injection and other advanced topics. But by doing this, you can programmatically do all sorts of interesting monitoring type activities to see what's being called, what events are happening. This could be useful if you're doing some analysis of malware, or any application really. And the last site that we're going to talk about is differential analysis or differential reverse engineering. This is actually quite a large topic, which we'll try to cover in moderate depth here. But the kind of the three main types of diffing that we're going to talk about is binary diffing, code coverage diffing, and looking at memory. So with binary diffing, this is where you're just looking at two executables. You could have more than two, but and you're doing a side-by-side comparison. And some of the common use cases for this would be if you're looking at patches or updates that are pushed down, you'd want to look to see, okay, well, what's the program before the patch was applied? How does it compare to the one that has been patched? And then by looking at the differences, you can examine, well, what if it was a bug that was being patched? You can quickly see, oh, okay, well, that may help you figure out what was the bug, and then how did they actually fix that bug. And so a few things to note on binary diffing is that, number one, there's many different views or levels at which you can perform this diffing. If perhaps the least useful, or in some cases the least useful, is just looking at a hex comparison between the two. So just looking at the low-level bytes, and that's because you'll lose a lot of context. I mean, if your diffing tool is not aware of the underlying instructions, then unless there's only a few minor changes, or something was just a few bytes were patched, there's a lot that you may miss just by doing that kind of a simple diff. If you go a level up and you're looking at the disassembled assembly and you're doing a diff at that level, now you're looking at things that's more useful. Things that, for example, the move instruction, which has many different opcodes which may have hex differences, now those differences would not be shown because now you're just looking at two different move instructions, even though they may disassemble to different opcodes. But shortcoming to this level is that if somebody's trying to prevent you from figuring out what was changed, they may do things like reordering the code, for example. Well, if you're doing a comparison, side-by-side comparison, reordering the code, having, for example, inserting unconditional jump statements to go back and forth between different sections, and doesn't change the underlying functionality, but it just makes it disguises those changes. So then there's techniques you can go further beyond that. One of the things that's used by a tool called BinDiff is, this is a commercial tool, is they compute something called a small primes product. So they assign each instruction a unique small prime integer, and for a given function they compute the product and they can compare that. So because they use primes and the uniqueness of that, when you're comparing a small primes product, then that's resistant to simple reordering, right? Because if you shuffle two instructions around, you haven't changed the product at all. And so there's a whole variety of strategies, and this can get pretty advanced, depending on what you're looking at. So it often in diffing, you may end up doing different kinds of diff or using a combination of tools. In some cases, you may be concerned about constants that differ. I mean, going into it, you don't really know what's going to differ, but you want to use a diff tool that has a variety of techniques to kind of give you the best result, and try to filter out the noise. In particular, if you're using this technique on a program that has either been obfuscated or there's been techniques specifically implemented to counter this type of analysis. I mentioned PiMay earlier at the beginning of this lecture. There's a tool within PiMay called PiMay Diff, and this does include a whole variety of algorithms that can be useful to you when comparing different executables. Code coverage diffing is also very powerful, and this is really nice, especially for large or GUI programs. The basic idea here is that if you run the program once and you're exercising functionality that you don't care about, then you run it again and you only exercise functionality that you do care about. By diffing the functions that were called between the two runs, filtering out the ones that show up in both or just the first run, you can very quickly isolate where in the program is the function that you care about the most. And so this is a way of zeroing in on that function or that piece of code without even doing any low-level analysis initially. This is just running the program and letting tools do the work for you to create this diff. So to illustrate this one, we're actually going to walk through a few screenshots to demo this technique. So in this case, we just want to find the about. What function invokes the about information in this Notepad++. So a few stats here, over 3,200 functions, almost 29,000 basic blocks, and out of all this code, there's only just one or two functions that are dedicated to the actual about window. And so our goal is we want to find this and then make some small changes to illustrate that we did. So to do this, we're going to use leverage PiMay, and there's a PIDE dump script that comes with PiMay. So after you've disassembled your program in IDE Pro and it's finished its auto analysis, you can run this dump script, which is basically going to create this .pide file, and then the analysis is going to be done under that. So we're going to run that. Name our output here. So we have our .pide output. And then what we're going to do is we're going to create two tags. We're going to create a filter tag, which is where we're going to run everything that we don't want. And then we're going to have an about tag where it's just where we do want. This is where we're just going to essentially click on the about window. And so, as it's pointed out here, there's going to be other GUI functions that are going to be run, but these also should have occurred in the filter tag. And so this should help us zero in on what we want. So we're going to first do the stalking here on filter. Now, by stalking, process stalking is a technique that was presented by Pedram Amini at a Recon conference many years ago. And the general idea is that you can set all these breakpoints for all the functions in the program. And so as you run under debugger, every time the breakpoint is hit, you know, okay, this is a function's call, and so you can essentially log all the different functions or all the different breakpoints that were hit, and that kind of gives you an idea of what functionality has actually been exercised. So it's a clever technique and extremely useful for doing this type of task. So we look at our PiMay console here, you'll see all these debugger hit and then some address. These are all functions that are being hit when we're running various functionality in this Notepad++ program, everything except for, of course, the about. And you can see in the target listener here we have about and filter. So this is under the filter. So now we're going to set, now that we've captured all that, we're setting the filter as our filter tag. So basically what that means is that now when we run and stalk the program, in this case we're stalking specifically about, it's going to be filtering out all the functions, all the that was captured in the previous run are going to essentially be ignored. So those are being filtered this time. And so now the only breakpoints that we should see hit are the ones that are associated with specifically about. And so if you look at the window here down the bottom, you just see 3 debugger hits. The last of which was 48DD10, which we'll look here on the next slide. So we've loaded our output into UDraw, and you can see there's the sub 48DD10, and you can see which functions that it called, which are clearly drawing functions for displaying the about dialog box. Okay, so that looks interesting. So now just to kind of put a quick patch in, this isn't anything particularly useful, but we're going to change the code here to move this JoJo rules string in, and so that's essentially the change that we're making. And so now when we look at the Notepad++ and we run the about, under author and homepage, you now see this string JoJo rules that we just inserted. So this was just kind of a simple example to walk through, but illustrating how easy and quickly you can, by using code coverage tools and diffing the different runs, zero in on the functionality you care about. And like I said, for GUI programs in particular, this is nice because you can be precise about which functionality that you are actually executing. And that's it. So if you have any questions, again, send us an email. There's a lot of great references out there. This is meant to introduce you to reverse engineering, but to really master some of these techniques, you need to just get practice. And so as far as references, Windows internals, is a great book. It has everything about Windows that you want to know. The PiMay reverse engineering framework, I'd highly encourage you to play around with that some, get familiar with that. IDE Pro, um, IDE Debug, all these tools, try doing some remote debugging. Maybe try, if you're interested in crash dump analysis, give your hand at that. Just try examining some of the kernel memory. All these things, as you get some exposure to, will help you realize, once you understand how to use a capability, then when you're given a particular problem, it will help you figure out the best way to go about solving it. So that concludes this lecture. Thank you very much.